Alright everybody, welcome to the lecture video for Chapter 12 in your book, Solids and Solid-State Materials. And I have to say, we're only going to cover a portion of this chapter. If we don't go over anything in this video and it doesn't appear in the Chapter 12 and 13 homework assignment on Mastering Chemistry, you won't be responsible for it on the test. With that in mind, we'll jump right into this by talking about how we can categorize solids in chemistry. One of the most basic distinctions is between amorphous and crystalline solids. Amorphous solids are those where the particles are arranged randomly without any long-range repeating pattern. Rubber is a good example of such a substance. As opposed to amorphous solids, crystalline solids are those where the particles have an ordered arrangement that repeats in three-dimensional space. This encompasses most ionic and molecular solids, as well as metals and a type of solid that you probably won't have come across before, called covalent network solids. Here we can see a couple representative examples of crystalline and amorphous solids, amethyst and rubber respectively. If you look closely at the amethyst, you can see that the faces of the solids are smooth, geometric shapes. This is often an indicator of the fact that the solid is geometrically ordered on a microscopic level as well, which it is as a crystalline solid. Here's a chart that gives a good summary of some of the basic properties of the four types of crystalline solids mentioned earlier. Ionic solids, which are held together by the electrostatic attraction between the negatively and positively charged ions in the lattice, tend to be brittle, hard substances with high melting points. Any compound you can think of that consists of cations and anions would fit into this category. Molecular solids are held together by the categories of intermolecular forces discussed in the previous chapter: dispersion forces, sometimes dipole-dipole interactions, and sometimes hydrogen bonding. Solids composed of individual covalent molecules held together by these intermolecular forces tend to be soft, have relatively low melting points, and they tend to be poor conductors of electricity and heat. Examples include things like water ice, dry ice, and most organic compounds. It's important to make the distinction between molecular solids, where the individual molecules are held together by covalent bonds, but the molecules themselves are held together by intermolecular forces, and covalent network solids. In the latter, there is a network of covalent bonds throughout the solid as opposed to isolated individual covalent molecules. These have very different properties. They are hard, high-melting substances, and examples include diamond or silicon dioxide, which is the chemical name for sand and also other silicate minerals like quartz. Finally, there are metallic solids. These consist of an ordered array of atoms held together by metallic bonds, more on what that means later, and any metallic element on the periodic table could fall into this category, as well as combinations of different metals, which are known as alloys. Metals are almost all good conductors of electricity and heat, although they have extremely variable hardness and melting points. Let's see what some of these look like on the molecular level. Sodium chloride is a go-to example of an ionic compound, and the structure of an ionic solid as well. If you look at the diagram of the positions of the green chloride ions and purple sodium ions, you can tell that they pack together in a relatively simple repeating pattern, as we'd expect for a crystalline solid. And if we look at a large crystal of sodium chloride on the macroscale level, below, you can see the geometric face structure that manifests as a result of the ordered structure on the microscale. Here's a diagram that shows how water molecules are held together in ice, a molecular solid. The solid lines represent oxygen-hydrogen covalent bonds within individual water molecules, and the dotted lines show the hydrogen bonding intermolecular forces between the oxygen atoms of one water molecule with the hydrogen atoms of a different water molecule. And overall, you can see the repeating 3D pattern intrinsic to a crystalline solid. The arrangement of atoms in silicon dioxide shows how covalent network solids exist on a microscale level. The diagram on the left shows how the red oxygen atoms are positioned around the gray silicon atoms in a tetrahedral molecular geometry. We can represent these units as red tetrahedra, where the vertices of the tetrahedra represent oxygen atoms. The silicon atoms are at the center of each tetrahedron. On the right, you can see how these things are arranged. We have an ordered pattern of tetrahedra that share vertices. In other words, the silicon centers are linked together by shared oxygen atoms. The pattern continues indefinitely in all directions, creating a single, giant array of covalently bonded atoms. and metallic solids like iron have a pretty unique structure that we'll see in more detail later on. As with most things in this class, you might wonder how we can know about these things I just explained when it's all happening on such a tiny scale, too small to see even with a microscope. Without getting into the hairy details, let's talk a little bit about how we can know how atoms in a solid are arranged: X-ray diffraction and crystallography. X-rays are high-energy electromagnetic radiation with much shorter wavelengths than visible light. However, the wavelengths of X-rays are comparable to the distance between atoms in a crystalline solid, on the order of about 1/10 of a nanometer. Like all electromagnetic waves, X-rays can interfere with each other constructively or destructively. Constructive interference happens when the waves overlap in phase with each other, amplifying the wave. Destructive interference occurs when the waves are out of phase, which causes them to cancel out. Diffraction is what happens to electromagnetic radiation when it is scattered by an object with regularly spaced structure, like a diffraction grating, prism, or, in our case, atoms in a crystalline solid. When X-rays diffract off a crystalline solid, measuring the angles at which the rays constructively interfere provides information about the spacing of atoms in the solid. Doing this along multiple axes in 3D space and acquiring all spacing data along all of these axes provides a full picture of the repeating pattern or structure of the solid under study. This information can be deduced using the Bragg equation, which is shown here, but which we will not use in this course. We're going to skip over the sections on unit cells and the structure of ionic solids to briefly mention some more details about covalent network solids. For this, we need to talk about allotropes. Allotropes are, simply put, different structural forms of the same element. For example, carbon is an element, but both graphite, which is used in pencil lead, and diamonds, which are used in jewelry, are both made of pure carbon, but obviously have wildly different properties. A look at the crystalline structure of both shows us the underlying reason for the difference. In graphite, there are flat planes of carbon atoms arranged in hexagonal arrays called sheets, held together by covalent bonds. Between these sheets, however, there are no covalent bonds, only intermolecular interactions. By contrast, in diamond, the carbon atoms are held together in a repeating pattern of covalent bonds with tetrahedral molecular geometry around each carbon atom. This array of covalent bonds extends in all 3 dimensions throughout the solid. As a result of these differences, the 2 forms of carbon have very different physical properties. Graphite is a soft material, hence its use in things like pencil lead, and a very good electrical conductor. Diamond, by contrast, is one of the hardest known materials in the universe, and it's an extremely good electrical and thermal insulator instead of conductor. There are 2 less common allotropes of carbon shown here, fullerene and carbon nanotubes. These are researched a lot in nanoscience, but have few real-world applications. Carbon nanotubes in particular are interesting for their extreme physical strength, but they're very difficult to manufacture on a large scale, which has limited their applicability to any sort of real-world problem. As a side note, carbon is not the only element with multiple allotropes. One remarkable example is tin, which has 2 main allotropes, white tin and gray tin. The 2 allotropes are so different that white tin is a metal, while gray tin is actually a semi-metal, more like silicon, for instance. This makes tin unique on the periodic table as an element that, depending on its form, can be either a metal or a semi-metal. Allotropes can apply not only to elements, but also to compounds as well. Silicon dioxide, sometimes known as silica, is another covalent network solid, in this case a compound rather than an element, with multiple allotropes as a compound. Depending on its form, it can exist as quartz, sand, glass, or many other forms found in different minerals as well. As promised, let's come back to metals. The way atoms are held together in these solids are pretty unique compared to everything else we've looked at. The bonding between atoms in a metal is often referred to as an electron sea, where an array of metal cations are immersed in a sea of delocalized electrons that can freely move throughout the structure of the solid. You can imagine how this free movement of electrons facilitates the strong electrical conductivity that is seen in most metals. There's a lot of interesting discussion in this chapter on other types of materials, semiconductors and their applications in devices like light-emitting diodes, including LED bulbs, and things like solar cells, as well as some discussion on the fascinating subject that is superconductors. But the only other topic we're going to cover here are ceramics and composites. Feel free to read through some of that other information in your own time if you're inclined and are interested in how some of these modern devices work. Ceramics are a class of non-metallic, non-molecular solids that have certain shared physical characteristics. In particular, as you can see by looking at this chart, ceramics all have very high melting points and very high hardness. This is true for a wide variety of ceramics, including the ionic oxide ceramics at the top of the chart, and the non-oxide ceramics at the bottom. Comparing the values on the previous chart to those of some common metals, say aluminum and steel, you can see that the ceramics are much harder and higher melting, while having a density much lower than that of steel, and roughly similar to that of the much less dense aluminum. Ceramics also tend to have a much higher elastic modulus, or essentially they're much stiffer compared to metals. So in summary, ceramics have higher melting points, are stiffer, harder, more corrosion resistant, and better capable of maintaining their strength at higher temperatures when compared to metals. However, due to their higher hardness, ceramics also tend to be more brittle than metals, which are usually quite malleable. Like I said, there wasn't a whole lot to cover for Chapter 12, so this brings us to the end of the chapter. Because we didn't cover a whole lot of subject material in this chapter, the homework for Chapter 13 will include some problems from Chapter 12, as opposed to there being a separate homework assignment for Chapter 12. Take care, and make sure to stay safe.